Hello everybody and welcome to this video. We're gonna keep talking about chapter number 2. We were discussing in the previous video everything related to energy and energy interactions, and now is the time to define something very important, which is the first law of thermodynamics. One of the most important topics in the class. You'll be using this principle from now until the end of the semester. Okay, the first law of thermodynamics. It's something that you will be carrying for thermodynamics 2, heat transfer, and courses, and any courses that has temperature involved. So the first law of thermodynamics is also known as a conservation of energy principle. It provides a sound basics for studying the relationships among the various forms of energy and energy interactions. Based on experimental observations, the first law of thermodynamics states that energy can be neither created nor destroyed during a process. It only changes forms. And that's what is very important about the first law, the statement. Okay? And from now on, you have to memorize the statement. You're going to see this throughout the whole book, and it says that energy can be neither created nor destroyed during a process. It can only change forms. All right? Just remember that. So basically what it says is like when you have a process and the process has a stage number 1 and then a stage number 2, you will see based on experimental observations that the total amount of energy will be always the same. So at stage number 1, we have potential energy equals to 10 kilojoules, and then there's no kinetic energy because it's not moving. As soon as the rock goes, down the hill, then you're going to have potential energy equals to 7 kilojoules, and then kinetic energy equals to 10 kilojoules. But at the end, you're going to have the same 10 kilojoules. So the energy only change forms, from potential to kinetic or from kinetic to potential. And you're going to see all these interactions as you move into the book. So we study the different forms of energy, and in the past, we were talking about heat and work, and those interactions are part of what the first law is. It's staying. So, for example, if you take a look at the pot and you know exactly how much Q is coming into your system and how much Q is coming out of your system, then you can find how much energy it's inside of the pot, which is your system, the thing that you're studying. So you're taking into consideration external factors and then making a conclusion inside of your substance, which is the water. If we take a look at this guy right here, well, the same thing. You have an adiabatic environment and you have something going on inside of this particular device. You have something external that is giving you some work into your system, and therefore you can find the energy that is involved in this particular interaction. So more examples, when let's say on this particular one, we have a shaft that is rotating and generating or putting into your system the amount of 8 kilojoules, and therefore you can find if there's no interactions because it's adiabatic, no heat is coming out or in, then you can find that your energy is equal to 8 kilojoules. So you're using external factors to actually know what's happening inside of your device in a study. Same thing right here. If you have a work boundary done on the piston, right, then the cylinder will have inside a substance that you can easily find how much energy is carrying. So at the end of the day, what is very important on this and on all of this is that we establish an equation to study the energy, and pretty much we have the total energy entering the system minus the total energy leaving the system will be equals to the change in the total energy of the system. And that's what's very important, because at the end of the day, it's energy that comes in minus energy that comes out. It's equals to the energy of the system. And this equation right here, it's the most important to establish all the equations that we are about to solve. And if we read this statement, the net change, increase or decrease in the total energy of the system during a process is equals to the difference between the total energy entering and the total energy leaving the system during the process. Okay, so we have a very good example right here. We have, the work of the shaft equals to 6 kilojoules, and then we have some heat coming into my system, which is equals to 15 kilojoules, and then Q out coming out of my system is equals to 3 kilojoules. So what's happening? If we apply the equation, this one right here, we have that everything that comes in minus everything that comes out will be equals to your system. So what's coming in pretty much is 6 kilojoules. So my energy of the system, it's equals to 6 kilojoules from the shaft, right? Plus 15 kilojoules from the heat coming in minus 3 kilojoules coming in the form of heat. And at the end, that gives you a total of 18 kilojoules. Units, very important. And that's how you find in an easy and a very easy and simple way how is the energy inside of your system. So we just need to remember important formulas related with the energy change. And we were talking about, everything that comes in minus everything that comes out will tell us exactly the delta of the energy. But now we can also study something a little bit different. We can see it from another perspective and find the delta of the energy of the system as, energy that I have at the end minus the energy I had at the beginning. And that will give me another formula. So energy of the system will be equals to the final energy minus the initial energy, or E2 minus E1. That way you can find, the energy. When we are studying energy, we take into consideration internal energy, kinetic energy, and potential energy. We all should remember that from previous chapter. So I'm going to rewrite the delta of the energy as delta of the internal energy plus delta of the kinetic energy plus delta of the potential energy. All right, or potential energy at the beginning and potential energy at the end, internal energy at the beginning, internal energy at the end. Then just for you to remember, delta U will be equals to the mass that multiplies U2 minus U1, and delta of the kinetic energy should be equals to 1/2 that multiplies the mass times velocity at the end to the square minus velocity at the beginning to the square. And then delta of the potential energy should be equals to the mass that multiplies gravity and the differences between the height, basically. For stationary systems in which the system is not moving, delta KE and delta PE will be equals to 0, and therefore the only thing that we will need to study will be the internal energy. And don't panic yet, because you'll see that with the exercises. When they said about a stationary system, they talk about like pistons and cylinders and things like that. And now we're going to establish the energy balance for any system undergoing any kind of process that can be expressed as energy that comes minus energy that comes out. It's equals to delta of the energy of the system. Okay, and that's this one right here. It's pretty much the net energy transfer by heat, work, mass, things like that. And then this guy right here, it will be the change in internal energy, kinetic energy, potential energy, and any other energies. And if I want to rewrite that in a rate form, you remember what is very important about the rate. We only have to add the dot point, which is E dot in minus E dot out will be equals to the delta of the energy of the system. Something very important, the units for this guy will be kilojoules. The units for this one will be kilowatts. All right. So the energy can be also expressed per unit mass. Everything is expressed in like the regular way, then per unit mass, then also in a rate form. So now per unit mass will be the little e in minus the little e out. It's equals to the delta of the energy of the system. And what's a unit for this one? If it's per unit mass, it'll be kilojoules per kilograms. Okay? And remember, I told you that in the beginning we have energy, energy rate, and energy per unit mass. So then energy balance for any system undergoing any kind of process. And again, I'm going to rewrite this equation because it's very important. It'll be as energy in minus energy out will be equals to delta energy of the system. So we need to remember, or we need to know, if you read the book until now, you probably know this already, but the mechanisms for energy transfer will be heat transfer, work transfer, and mass flow. All right? Mass flow meaning like, the energy that the system is carrying as a whole, substances and things like that. A closed mass system involves only heat transfer and work, okay? When there's no mass coming into your system. When you have, for example, a pump that is pumping water into your system, then mass flow will be, included. But then if I want to rewrite the equation, it'll be something like this. Energy that comes in minus energy that comes out will pretty much tell me delta of the energy of the system. But also, it'll give me something like this. Q in minus Q out. Plus, now we go with work. So we already did with heat transfer. Now with work, it'll be work coming in minus work coming out. Now work, it's done, plus energy of the mass coming in minus energy of the mass coming out. And that's all of that is also equals to the delta of the energy of the system. And I'm going to teach you how to simplify those equations, but that will depend on the case. There are going to be some cases in which this whole thing will be equals to 0, or this whole thing is going to be equals to 0. But at the end of the day, we just want to keep it general so we can utilize the formula for any particular cases. When we have, when we have thermodynamic problems, it's a matter of putting the puzzle together. You will have data, but you will not be required to use all the data you have. Probably if you go option number 1, then you will use less data than if you go option number 2. So at the end, you will get to the same point, through different paths. And I'm okay with any one of them. I actually appreciate that even more because I can see that you're developing your design intent. And as mechanical or chemical engineers, that's what you need to keep moving. So energy, the energy content of a controlled volume can be changed by mass flow as well as by heat and work interaction. So this is something, a system that this formula will work perfectly fine because you have mass interactions, you also have work in heat. Okay, but again, that will depend on the particular system you have for each case. All right. Efficiency, okay. Everybody knows probably what efficiency means because you've been working with that in other classes. So efficiency is one of the most frequently used terms in thermodynamics, and it indicates how well an energy conversion or transfer process is accomplished. Efficiency is equals to the desired output over the required output, okay? So you have something like, let's say, compressor, right? The compressor will essentially will deliver some work, right, or some energy, and that energy should be equals to X number. The compressor will require some work in order to deliver that energy, and the difference between those two will tell you how efficient is your device. And that's very much important because when you have when you have it's very important, because when you have your engineering devices, you need to know exactly how much energy you actually need to produce another amount of energy, okay, or how much energy it's pretty much delivering over the amount of energy that your system is requiring, okay. So that's why you always are going to have a desired input and a required input. Let's say you're designing for a system, and then you do your calculations, and turns out that you need a machine that is able to give you, I don't know, 1,000 kilojoules of energy, okay. First of all, what do you do as designers? You will find the machine that you need. Once you know whether it's a turbine or something like that, okay, then you need to go into the catalogs for turbines, and you need the ones that will produce that amount of energy. That will be attached with something that is required in order to run the machine. So both of them combined will tell you how efficient your system will be. And therefore, when you are presenting your work to somebody else, you can say, I have a generator that is efficient as much as, I don't know, 90, 80%, things like that. Efficiency will be pretty much given in the next chapters, chapter number 5, when we start developing the different engineering devices that we have in the industry. For example, the efficiency of a water heater is the ratio of the energy delivered to the house by hot water to the energy supplied by the water heater. Again, you need some amount of hot water coming to your house, but you also need some energy that will make you produce that heat water that you need, okay, that hot water that you need, sorry. Efficiency of mechanical and electrical devices. So pretty much it's the same equation that we had before, but now we're going to add the mechanical work. So mechanical efficiency is equals as the mechanical energy output over the mechanical energy input, okay? Or if you want to see it as this one, is the desired output over the required output. It's exactly the same thing. So mechanical energy that I need to be generated versus the mechanical energy that your system will need. The efficiency, the effectiveness of a conversion process between the mechanical work supply or extracted and the mechanical energy of the fluid is expressed by the pump efficiency and turbine efficiencies, okay? We always use that. And why is that? Because the pump will actually be the opposite of the turbine. The turbine will use the water going into the turbine to generate some energy. The pump will require some energy in order to give energy to that fluid, okay? And this is giving, it has, sorry for this presentation, these guys right here are not right. So in terms of the mechanical of the efficiency for a pump, right, I will have the efficiency, sorry, let me just go like this. So efficiency of a pump will be equals to pretty much delta E of the mechanical fluid over the work required by the shaft. Okay, in other words, it's pretty much the work that the pump is producing. Remember, always desired input or output over the required input, okay, which is the work that the pump needs. Okay, so this one is the work of the pump that is delivering into your system over the work that is required by the shaft in order to work. With the turbine, it's similar. So efficiency of the turbine, okay, it's equals to the mechanical energy output, which is the work of the shaft, over the mechanical energy decrease of the fluid, which is the delta of the energy of the mechanical fluid. And this is not more than the work given by the turbine which is expressing energy and the mechanical energy of the turbine as well. This is different now because now this is coming in and this is coming out. Okay? So just remember that because it's very important. And we always use the turbine and the pump because they're different from one another. So the pump will actually give energy to the fluid, and the turbine will use the energy of the fluid in order to generate electricity. Okay? So, like I said, pretty much they will come from the same equation. And what equation is that? Efficiency it's equals to the desired output over required input. Okay, that equation will work for all efficiencies, guys, not only for pump or turbine, for sure. Once you understand what the pumps are, or how the turbine will work, then we can establish which one is desired and which one is required. Okay. Something important, and again, in the book that will be explained in this chapter, but this is just, like I said, an introduction. Okay, and it's when you have two components connected, right? And you need to know exactly how much is the efficiency of the whole system turbine generator. You're gonna have an efficiency for your turbine and efficiency for your generator. Okay, the efficiency of the whole system as a system will be the multiplication of the efficiency of the turbine times the generator. So 0.75 from this one and 0.97 will give me a total efficiency of 0.73. This topic will be developed in chapter number 5. So if you didn't understand exactly, or you didn't have the idea of the efficiencies right now, that's fine, guys, because we're going to develop those once we reach chapter number 5. Okay, we're still developing equations, we're still developing terms and definitions. Okay, so with that, that's the end of chapter number 2. Again, there's more information in the book. There's more information in my notes. So now you have my notes, you have the presentation, you have the book, and you have homework to be done. Okay, well, guys, that's all for today. Thank you very much for your time, and I hope these will help you.